Good morning, everyone. Oh, sorry. Like comes here. Our work is about fine-grained concept linking using neural networks in healthcare. My name is Jian Dai from National University of Singapore. It's a joint work with Meihui Zhang, Gangchen Jufan, Qingyuan Lim, and Professor Binqing Wei. First of all, I would like to introduce the background and motivation of our research program. Well, it is widely accepted that the use of historical medical records in a database is very painful. First of all, different doctors often have different writing style, including different textual descriptions of the same medical phenomena. In addition, the medical standards change over time, leading to word descriptions. Leading to word descriptions between the textual descriptions of the same medical phenomena as well. In practice, doctors often have to incrementally create a data set that he or she is interested in. Initially, a doctor may use some keywords to query a database. What happened here? And get a result set. However, he usually needs to remove some irrelevant records from the result set and use newly found keywords to invoke another round of database querying and the result set inspection. After many iterations, he may get what he really wants. Even so, once a new medical standard is released or a new writing style is detected in the database, a previously created result set calls for further curation. Therefore, an effective and automatic approach is long awaited by hospitals to improve the data usability. This motivates us to devise neural network linker, a neural concept linker that links the textual attributes in a medical records to a unified concept ontology so that doctors can easily query them by their codes instead of the raw text. Actually, the difficult here is that we can see actually the doctors have used their expertise in the data curation. How can we model their expertise or use the domain knowledge in the neural network? I think it's very challenging. Here is a big picture. NCL is part of DICE, which is short for Data Integration and Cleaning Engine. Actually, the DB group led by Professor Binqing Wei have developed a software stack that is Jian Dai for in-depth healthcare data analysis. Currently, Jian Dai consists 6 subsystems. DICE ensures the data availability and quality. CDAS effectively use cloud intelligence. EPIC enables big data processing. And Singa offers the distributed machine learning capability. Kohana facilitates online data analysis and IDAS visualize data. Jian Dai has been used by several real-world hospitals already. In this talk, I shall focus on the neural concept linking component in DICE. If you want to find more, please visit this website. To make it clear, we formally define our research program. We introduce the term query. We abstract the textual description in a medical record as a query. Formally, a query is defined as a word sequence. Concept is defined by 2 attributes, CID and DC, where CID refers to the unique identifier or code for the concept C, and DC refers to the canonical description of C. DC is also a sequence of words. A concept ontology C organizes concepts in a tree structure using sub-concept relationships. If a concept has no subconcept, we say it is a fine-grained concept. We define our research problem as a fine-grained concept linking. Given a concept ontology C and a query Q, it aims to identify a concept, a fine-grained concept that most likely generate a Q. Because you know that a concept can be described by different descriptions. Next, I want to present the challenges and the related work. Well, is it a difficult problem? Yes, we think so. And we summarize the difficulties of healthcare concept linking into two challenges. First, severe word description. As discussed, a healthcare text snippet can be significantly different from the corresponding canonical concept description. Also, there is a large semantic meaning overlapping between similar concepts, because concepts are organized by a hierarchy ontology. So the concepts from adjacent branches in an ontology often have the semantic meaning overlapping. Are there any available techniques can successfully address the above two challenges? Well, we classify the simile-permission techniques into three categories. First, the dictionary-based approach. These approaches rely on the constructed dictionaries to accomplish term to concept matching. Well, these methods exhibit good performance in some medical text. However, since the medical-related terminology is constantly evolving and the real-world text snippets are highly noisy, building a comprehensive dictionary is unfeasible. There are some machine learning-based approaches. These approaches depend on handcrafted features to build shallow models such as logistic regression or conditional random field, and use these models to classify queries into different medical concepts. These methods act as a soft stream matcher that can deal with some terms not included in the dictionary. However, they can hardly adapt to different scenarios because of the handcrafted features. Further, when the number of the involved concepts grows, their classification accuracy may drop sharply. Besides, there are some combined annotators or linkers. These annotators combine multiple annotators that may complement each other to improve the overall annotation quality. Our argument here is that as a concept linker, the proposed NCL can also be combined with the other annotators. Next, I shall introduce our neural concept linking framework. In NCL, we propose to perform fine-grained concept linking by an encode-decode process based on our neural networks. On one hand, an encoder encodes a fine-grained concept C into a hidden state. That is a numerical vector. On the other hand, a decoder computes the probability of generating a query Q from the hidden state, along with two designed contexts that use domain knowledge and expertise. At the heart of NCL, a new neural network architecture that is composite attentional encode-decode neural network COMAD is designed to realize the encode-decode process. In particular, COMAD is trained in an offline manner and used by online concept linking. Optionally, when NCL is unsure of the linking quality, the re-ranked concept will be forwarded and pulled for the domain expert's feedback. To capture the core meaning of a concept by the encoded hidden state, we use the description pairs to train COMAD. A description pair, CQ, consists of two text snippets with respect to the same concept. Here, C refers to the canonical description of the concept, and Q refers to its alternative descriptions. Q can be extracted from a knowledge base, such as UMLs, that contains different descriptions regarding to a concept. Since COM-add is a core component in NCL, I shall spend 6 pages on explaining it. The encoder in COM-add is essentially a function that maps a concept into a d-dimensional numeric vector. That is the hidden state. We achieve this by a recurrent neural network consisting of long short-term memory units. The decoder in COM-add takes as inputs the hidden state and the query queue and computes the probability of generating Q from concept C. Similar to encoder, the decoder utilizes LSTM units to decode the word sequence of query queue. That is, it decomposes the probability into a series of probabilities. To compute each decomposed probability, the textual context and the structural context are considered. In particular, text-based attention is used to incorporate the textual context into the decoding process. When decoding a query window, a query word, WT, we introduce alpha TR as the weight of the attending to the R's hidden state encoded from the concept C. Further, to aggregate the effects of all hidden states, we introduce a textual context vector derived from each hidden state. In addition, structure-based attention is designed to incorporate the relevant concept hierarchy from the concept ontology into the decoding process. Specifically, give a depth beta and a concept C, a concept CL, where L means the level of the concept. The structure context of CL in the ontology is a concept path from CL to its extensor, CL minus beta. Similarly, we aggregate the effects of all the concepts in a path and introduce a structure context vector in the decoding process. COM-add constructs a composite vector by concatenate these three parts. The information from the currently encoded state, the computed textual context vector, and the computed structural context vector. Based on the composite vector, a nonlinear layer and a softmax function are utilized to produce the decomposed probability. We also draw a figure to help you understand the customized encode-decode process. In this figure, we can see that TCT is computed from all the hidden states of the concept C. SCT is computed from all the final hidden states of all the involved concepts. And STQ is computed from a recurrent neural network. Furthermore, the decomposed conditional probability is computed from a nonlinear layer that takes as inputs the concatenated vector. We train COM-add in two phases. First, we use unlabeled text along with the labeled text, including the canonical description and alternative descriptions to train the word embedding, or word representation, or word embedding for each individual word. Please note that the words here can come from the unlabeled data. In other words, the queries, meaning that all the encountered words should have their word representations. Okay. After that, we use the label data alone to construct the aforementioned description pairs and use the pairs to train command so that the command knows how to interpret a concept into different descriptions. As discussed, command use online concept linking. And we also, I will show some experimental results. You may find more in our paper. Here is experiment setting. We use 2 datasets and 2 ontologies. And the training data comes from both the queries and the description pairs extracted from the knowledge base. We also have 8 competitors, including Noble Coder, PK Dark, Move Distance, Doc2Vec, Sequence to Sequence, or command without texture attaching and command without structure attaching. We have evaluated the problems. Results show that results confirm the effectiveness of NCL and suggest that incorporation of textual context and structure context indeed helps the accuracy improvement. We also evaluate runtime with different configurations. Okay, here comes the conclusion. In this work, we have designed a healthcare concept linking framework, and the experiment studies using 2 real-world datasets show that NCL managed to produce accurate concept linking results and significantly outperform state-of-the-art techniques. Thank you for your attention.
Can I ask if you have got any chance to compare with some other concept matching work like ConceptNet and the recent embedding methods for concept hierarchies?
Actually, we haven't found any.
It is not in this list, so that's why I'm wondering.
Not in this. Yeah, we haven't found such related work actually. Yeah.
Thank you.
Sorry.
So in your evaluation, you use quite comprehensive data sets for doing the comparisons. So I wonder whether you can make at least a subset of these data sets available for other researchers.
You may find more on the website I provided before, yeah.